we'll go into the class today's class, that is statistical test for checking the hypothesis. What is hypothesis? Can anyone say? We seen many machine learning algorithms. So now we should be in a position to say what is hypothesis, right? What is hypothesis?
Final output.
Oh no, surely not. Final output you mean y cap? No, y cap is not. I don't mean that y cap is hypothesis. What is hypothesis? Hypothesis is nothing but the way in which we approach a particular solution. I mean, for example, my hypothesis for linear regression can be that parameter estimated mx plus c can be the hypothesis. Whether my hypothesis works or not will be my error. If it is not working, I will get some error, right? Now, assume that some person is there called some Mark, right? Some King Mark
Or
Marks.
approximate values, sir.
Yes, come again.
Approximate X.
Yes, it's just an equation to model my input and output. How my output can be obtained with my input, my assumption. I can be my hypothesis. Now, assume that a person Marx is there. He is an industry person. He is willing to start a business, a new business. A new business is there. Now he need to understand whether he will get profit or not. A new business, and there is also some existing share in the same area. Already some old shops are there. Assume if he is willing to start a new shop, and he need to identify whether he will get profit or not. Just an assumption, right? Now his hypothesis says that, so he is actually having some brain, and his hypothesis says that he will actually get more profit, and the old businesses will be vanished. That is one kind of hypothesis. That is, he will get more dollars. That is, he will get more dollars, and they will be getting some question mark that they will not get anything. This is one kind of hypothesis. Other hypothesis is he will get a loss, and they will get more dollars. So this is the two kind of hypothesis assume for a business, right? Now, now what we have to do is, now being a machine learning analyst, what we will do, we will take some history of the number of shops came in that particular area, what kind of shops, what is the income of the people over there and that particular locality. Everything will be taking. We will be analyzing that. We will prepare a model and say whether a new business in this locality can be started or not based on the competition. So that is actually the thing. Based on our hypothesis, we can say that Marx can start, and somebody will say Marx cannot start. Both is actually there, right? So, so we need to do anyone. Now, if the data is large, that we know that if there are more number of data in the available table of history, right? In the history, I'm having more number of data, then surely my hypothesis may be correct because I have more number of data to study, so that my thing is, or my value also will be what I predict will be correct. But if my data is less, what will happen? Surely my prediction may go wrong, right? In that case, I will be in a position to judge two things. One is null hypothesis, another is alternate hypothesis. These are these both are most important terms in machine learning. What is null hypothesis is hypothesis that is false. I actually can term it as null hypothesis. That is, and the alternate hypothesis is nothing but hypothesis that is proven. Hypothesis that is false means, in the sense, I am trying to predict something, but it doesn't work. For example, initially we said that Marx will not get any profit; he will have a loss. But suddenly, after starting, he got some profit. It means that we have, my hypothesis that Marx will not get any profit is false. I term it as null hypothesis. And the other is alternate hypothesis, an exact opposite term of null hypothesis. That is an alternate hypothesis means that if, and if I say anything as null hypothesis, I immediately say that the counterpart of this will be a proven statement, and I call it as alternate hypothesis, right? Now, can you understand the gist of what I'm coming to say? Whenever we start any machine learning problem, the thing that will come to our mind is the hypothesis, how to frame the hypothesis. We will use many machine learning algorithms starting from simple linear regression to a very high unsupervised algorithm. We will produce some hypothesis and do the predictions. Many a times it may go wrong, and I call those as null hypothesis. But for example, I say, if I take age of the students, initially, for example, I take the age as uh, I take the text sorry, right. I'm saying that age can be 22, 23, 24, 26, 27, and it is going like that. 18, 16, uh, 29, 31. Right. Assume that I'm having something like this, and I need to do some kind of analysis here. Right. If I do an analysis here, can anyone say what is the mid portion of this entire distribution? What is the mid portion? What is the mid portion in this entire distribution? Mid in the sense, what is the mid value? Can anyone say? I'm having age of around 1, 2, 3, 4, 5, 6, 7, 8, 9. Age of 9 people is actually present here. In this 9 people, what is the mid value I can take? Students, can you hear me?
23, sir.
Okay, 24 I will take. If I take 24, what will happen? 22, 23, 18, 16, those things will be having fall here. 23, 22, 18, 16, everything have a fall here. And after 24, I'm having 26, 27, 29, and 31. And somehow, based on the y-axis parameter, I can have a normal distribution on this particular curve. Am I right or wrong? I'm having a normal distribution. We know that whenever a distribution is having a normal criterion, it means that it is actually doing good and it is actually fit for doing any kind of analysis. But here there are 9 kind of samples. Even 9 is a very small sample size. Now for this sample, randomly I'm picking some 5 samples from this. Say for example, that samples are going to be 22, 18, 16, uh, some 31, and yes, 22, 18, 16, 31, and also 29 also. So I take those things. Now if I have the same thing for that, we know that it is actually normally distributed at 24. And if I actually have this distribution again into control, randomly taken, below 20 24, I may have something like 22, 18, and 16. And assume that I'm having some other samples like even more than that, or here I can add 23 also. It will be like 23 over here. It will not be exactly normal distributed. It will be like this and it will be like this. The normal distribution actually vanishes here. I will not have entire symmetric operation on both left and right hand side. If the sample size reduces, I may have a very huge distribution, and I call that particular distribution as normal. When I take a random set of samples from that entire distribution and say it is also a normal distribution, at that time my hypothesis become wrong. So this is why the machine learning algorithm actually fail. Not I repeatedly say, right, when the machine learning algorithm fails, it is not with respect to the algorithm alone. It may be with respect to the inputs what you have taken. It may also be with respect to the hypothesis what you have taken and the input data. Suddenly, if you decrease the number of input data, and if the original sample is normally distributed, the original population is normally distributed, it is not that the sample is also should be normally distributed. The sample may not be normally distributed. At that time, if you apply the hypothesis of the original population to the sample, surely the sample will not give you good result. So those things we need to identify when we go for machine learning algorithms, right? I mean, making good what why we are going for statistical test. If I take a very huge history of population and assume some hypothesis for that population, It is not that the sample which I take from that population and work also should follow the entire characteristics of the full population. Surely it will not satisfy. So we should be in the position to identify whether this sample is good for analysis or not, because selecting samples is most important in making my model to learn, right? So I need to categorize the hypothesis in such a way that my sample is also working good, right? Now am I making it clear why we go for these kind of statistical tests between the original population and the new one sample? Yes. So assume that there is some person and he is going to start some business. So what is the thing is, he is actually asking a machine learning scientist that whether I can start a business here or not. The machine learning scientist said to him that if you start here, you may get a huge kind of profit, because the old companies are not that much good, you cannot get good profit. So that is a thing given by the machine learning scientist based on his hypothesis, his assumption you may call, or his hypothesis you may call if it is an algorithm. Now Mars is actually understanding that he will get more profit and the old company may vanish. So another thing is, if he started and suddenly the company went to a loss, it means that it is actually alternate that which is happened, which is said by the machine learning scientist, right? Why? Because the data what is taken for preparing the hypothesis is actually a different population from history. The data which is came new is the sample, a very small sample. So there will be a difference between the distribution what is followed for the original population, that is a very large number of historical data, and the sample which comes into play for testing. So there need to be understand what is null hypothesis and what is alternate hypothesis. This is actually not a direct definition. Whatever is categorized as null hypothesis, we should be in a position to reject that null hypothesis, and opposite to this will be the alternate hypothesis. For example, for Marx, if he thinks that he will not get if he thinks that he will get more profit, but afterwards he found that there is no profit for him. So the hypothesis that he will get more profit becomes null hypothesis, and the alternate to it, that he will not get any profit, becomes the alternate hypothesis, automatically proven, because this is proved, so this is automatically proven. Now we need to understand, given a very large set of data and a small sample, are the values of the data in this particular instant of time, and after some time we should be in a position to say which whether it is null hypothesis or alternate hypothesis. We should be in a position to judge that. Another way in which I give the this definition is, for example, if I have age of several people over here, and for these people I found that it is normally distributed. Why? Because if I place 24 here to the left on some kind of parameter over here in the y-axis, I can plot them in a normal way. This entire distribution is in normal distribution. But this distribution may be 9 samples here, but in original there can be 900 samples. I say that 900 samples as normally distributed. And if I randomly take some 5 or 10 samples as normal distribution, because they are not that much big. So there should be an hypothesis way. This sample can be taken or not. So we need some statistical test to identify what is null hypothesis. Yes, now we will practically see in Excel sheet and how it is actually going to work. Right now, I'm having a set of students. Previously, what is their identification, and after some predictions, what is their identification? Both we are going to take and apply something called as students T test. Right, this student T test is actually nothing but it's not for students. The discoverer of this T test is actually having some name, and that particular person don't want to reveal his name to the statisticians. So he want to keep some other name. So the name given is students, and actually this is popularly called as T test. T test actually popularly called as T test. Now we are going to see this and how to test, and we need to judge how what is the null hypothesis and what is the alternate hypothesis. Right, we will be doing it in Excel, and once done we will be going into the practical and see it directly and how that is actually working. Right, now we'll see here, and before looking into it, I'll say one additional term, that is this T test also consists of something called as T table. Based on the T table only we can able to find that whether the hypothesis is correct or not, right? We need the use of t table also. And two types of testing is also there. One is one tailed t test, another is two tailed t test. Everything will be seeing one by one, right? Now assume that I'm having five student samples. Five student samples are there. So before some testing or something, right, assume that I'm going to check whether this particular hypothesis for the set of students being given some training. Before training they are having some values. After giving some particular sports training or anything, their values may be increased, because once training is given, their efficiency will increase, right? So we are having both the things. So now we will see how it is going to actually work. Before training, the value of student 1 is 0, 2 is 2, 3 is 1, and 4 is 2, and 5 is 1. You can have something random. After some testing, so what happens, the student's value is actually increased. Student 1 got 5, 2 got 8, uh, okay, 1 also, 3 also got 8, 2 will get 5, and some 1 will get 7, right? This is actually the sample what I take. For this sample, if I need a very small sample, for this sample, if I want to apply t-test, what is the procedure? Just take summation of all the pre-test and post-test result. Take the summation and take the mean also. Both the things I'm going to take. So let me take the summation, sum of all these particular values. I take everything. Similarly, I take sum of the post-test. I take the sum. I take the mean also. So this is the mean, and I take mean of the post test also. So far so good. Next we are going to apply it to some formula. For finding those formulas, we take this. So far so good, right? Am I making it clear?
Pretest means after predicting and post test means real values, sir.
Yes, it is actually in terms of machine learning, but we are not taking any machine learning over here. Just a statistical data set where before some hypothesis, a value is there. After an hypothetical involvement, another value came. That is what the assumption we take. So before giving some training to the student, he got some results. After giving a training, he got another result. So that is actually the kind here. So now we have the value here. Now we take the difference between post test and pre test. So this minus pre test. So this is 5. I take the difference of everything. I make the summation of this difference also. I take the summation of this difference, and I take the mean also. Similarly, I go for the difference squared. I run it for all, and we take sum of this all difference squares, and the mean also is raised. So we got the necessary input things we got. Now, like Shirdi asked one question, when we go for a machine learning criterion, how this table actually looks, right? So this thing is nothing but how we are going to approach this pre-test and post-test values. This pre-test values is nothing but, for example, if I run a particular iteration and I got some result. How, for example, assume that we are going a simple linear regression, and upon applying the linear regression, I got an equation y is equal to mx plus c. I mean it y cap is equal to mx plus c. I got an y cap value, and I apply an hypothesis to this. I found some errors are there, and after finding the errors are there, I need to apply another hypothesis to tune the error in such a way that my accuracy can be increased. So what happens, I need to apply another hypothesis. Maybe I can change the input phase, or I can do something. I can do some variations for this. I'll get another y cap, right? That is actually the post test, right? For example, you can also take it going to be a training and testing also. You can also take the entire distribution training value as well as the testing value, right? Those things also you can actually take, but for the same case, same inputs, that you actually take, and you have to analyze the t distribution. If you do this distribution, then you can identify whether your hypothesis is going correct or not. If we do this, we will have one question in mind. Then what is the role of error? If I change a hypothesis and if my error is decreased, then I can directly say that my hypothesis is correct. But if you are actually approaching a particular value, if you are changing the hypothesis, even though your error is decreasing, it is not that you have chosen a very correct hypothesis. If you chose another different hypothesis which supports you more, that is in the if I draw a plot, you will understand. If it supports more in the t-test, it means that your hypothesis is even more better than what you actually chose. If you chose a very good hypothesis, then what will happen is your error will go as managed as possible, right? So this is the thing we are saying. When you apply another hypothesis, and what is the result after applying that, if we need to find that, then t-test will be used. Not only t-test, many statistical checks are available. So today am I making it clear now for you?
Yes, sir.
Yes. Now we apply the formula for t-test. Now we are going for the two-tailed t-test. Two-tailed t-test. The formula is, and I need to write the formula in paint window. So the formula is nothing but I need to calculate the tail value, that is t. T is equal to summation difference. What is the difference I got between the post test and pre test? That is summation divided by whole square root of n into summation d squared minus summation d the whole square. Whole divided by n minus 1. I'll explain every statement in this formula one by one now. Right now, what we do here is, in bottom, you can easily understand what we have done. We are actually going via the variance, and we calculate this. That is n sigma the d squared minus sigma d the whole squared. Nothing but we are actually calculating the expected variance. And if I take the square root, I'll get the standard deviation. This n minus 1 corresponds to the degrees of freedom, number of observations that are independent. We have n minus 1, and on the top we have the total sum of the observations, right? This total sum of observations in one-tailed t-test, if you go, we can also take the mean on the top. We can also take the mean and then record those observations, and we need to center with the mean and the each individual parameters. That also we can actually do. This is actually the test formula. Now we will apply this particular values here, right? So I take summation d. So summation d is nothing but we have 27 here. I write it 27 whole divided by whole square root of n into summation d squared. N into summation d squared. That is number n is actually 5 and summation d squared is 155. So I take that. So it is 5 into 155 minus summation d the whole square. That is summation d is nothing but 27. We write it in the numerator also. So 27 squared whole divided by n minus 1. That is number of degrees of freedom. So n minus 1 is nothing but 4. We have 5 observations. 5 minus 1, I'll get 4. I'll do this calculation in the Excel sheet. I get like is equal to, if I want to calculate 5 into 155 minus 27 square, that is 46 I'm getting. So this is actually 46. This is nothing but 27 divided by whole square root of 46 divided by 4. So I will need to calculate this. 46 divided by 4, I get 11.5, and I take square root. This 3.39 I get that is equal to 27 divided by 3.39. It's what I get here. Is equal to 27 divided by 3.39 and I get 7.961. So this is what the t value I get, 7.961. So I get the t value here. T value I'll write here after applying the formula. T value is equal to 7.9618. I get this value 7.962, right? This is the value I get. So using this value, we are going to say whether this pre-test to post-test conversion hypothesis is going to work or not work. That is what we are going to calculate and see. Now what I go is I go to the distribution example. Now I take the entire distribution. Now I take it is going to be a two-tailed t-test. Two-tailed t-test and t is equal to 7.962 and degrees of freedom df is equal to 4. Next, number of observation is 5, so 5 minus 1 is 4. And confidence level, confidence interval. I can fix any confidence interval. Usually, you'll be having confidence like 90, 95% confidence on predicting this particular value, right? I say confidence interval is going to be 95%. So this value we are actually fixing, and based on this value, for this particular statistical sample data set, I need to check whether this sample hypothesis is working or not working. So what I will go, I'll go to the Google. Anyway, I'll take this table starting from the Google. So you can also take. I take to Google. Can you see my Google page?
Yes, sir.
Yes. Now I just type T table. So I'll get T table here. So T distribution table is here. We can also download the table and have one tail and two tailed T test table will be available here. Just click. And this table is actually for one tailed T distribution table and another is for two tailed. Two-tailed T distribution table is available here, and on this two-tailed T distribution table I'm having, right? See, the degrees of freedom is there on one side and the confidence interval is there on other side, right? Both things we are having. Now we need to find the value where our thing actually falls. Now what is our confidence interval? Our confidence interval is 95%. So how much we lack? 100 minus the 95, that is 1 minus 0.95. We get, what is the difference? We get 0.05. That is the confidence we actually lack, and we just take this into the intersection here. The degrees of freedom is 4 and the confidence we lack is 0.05, and the term which is actually intersecting both is 2.776. Am I making it clear? Are you able to identify how to check in the T table?
On చేశారు again.
Yes. My degrees of freedom is 4 and my confidence interval is 95%. 95% in the sense it is what? 1 minus 0.95. So it is actually the confidence what I lack here is 0.05. So in the T table, I have to check for the degrees of freedom versus the confidence lack. So my degrees of freedom is 4 and the confidence lack is 0.05, and where it is intersecting, it is intersecting in 2.776. I didn't do you able to understand how to fix it in the T table?
Yes, sir.
Yes. Now I go and draw the diagram. My diagram will be like this. This is two-tailed t-test. So one value will be used for two things. So let me draw the diagram and explain you how you should do this. So T always says that the original population is normally distributed. So this is actually the original population that is normally distributed. Assume that it is exactly centered. Okay. So this is a normal distribution, and what is the value we got here? 2.776. So 2.776 will be on this side, and this is minus 2.776. Since it is a two-tailed tree test, I can plot it on either end also, both left and right hand side also. This is 2.776 plus, and this is 0. Assume, right? So now I say one more thing here. This particular region, that is the region across 2.776 on both the ends, these are called as rejected regions or red regions. I call it as red regions. And if your hypothesis falls in the red region, it means that you should not take that particular hypothesis. It means that your hypothesis is null. And those values which fall here, let me take this. This is called as gray region. This is actually called as gray region, and your hypothesis is correct in this particular region. If your hypothesis falls here, then it is an alternate hypothesis. If your hypothesis falls after or 2.776 here or here in minus 2.776, it should be rejected because it is a null hypothesis. Now, what is the t value obtained? The t value what you obtained is 7.962. Whether it is in the gray region or red region. Whether it is in the gray region or red region.
Red.
Red. So, what you should do? Shall I accept the hypothesis or reject the hypothesis?
Accept.
A, it is in the red region. If it is in
Sir,
the red region,
reject చేయాలి sir అది. Actually, we need to
yes,
reject it.
yes, I need to reject this particular hypothesis because it is not in a gray region.
Variation.
If it is beneath this particular range, I can actually accept. So this hypothesis, we didn't fix what is hypothesis here. Based on some hypothesis, the initial values are taken and the next values are considered here. This hypothesis actually doesn't work for the original sample. How it is working? It is not with respect to the error. This actually with respect to the behavior of the original population. The original population may have some 100 records, but the sample what you have taken is maybe only of this this records. For that 100 records, this particular hypothesis is working, but the sample what you have taken, it is not working. The hypothesis is not working for this particular sample because this sample will not follow the normal distribution exactly same as the original sample population. It will never follow. So we need to, but we need to take sample in such a way that it is as closest to the original population, right? So this is the thing. So I need to, so what I would say, reject the null hypothesis. This is hypothesis, so reject the null hypothesis. This is actually called as the t-test. My t-value is actually greater than 2.776 and not falling in the gray region. So I should reject the null hypothesis, right? Now, the another question what comes to our mind is, sir, what we can do if the confidence interval is not fixed? Yes, you need not fix the confidence interval. You actually decrease the confidence interval. Based on the confidence interval only, this value will be fixed. That is one thing. It is always better to have 90-95% confidence for your statistical recordings. Another, if I increase the degrees of freedom, if I increase the degrees of freedom, surely what happens? It also will have a good effect in my algorithm, right? Because it is in the 46 divided by 4. So surely it will come in the numerator because it is in the denominator reciprocal. When I take it in the reciprocal way, this will become numerator. So what will happen? It will also give some good effect in my particular thing, right? So it is actually purely dependent on the number of observation and the confidence interval. The thing to understand here is t-test will work better when you have a minimum of 20 samples. Not only t-test, whenever you go for any sample extraction from a very big population, take a minimum of 20 samples. Below that, it means that you are actually biasing the particular statistical test. Surely you will get a rejection. Mostly you will be getting a rejection. So when you get more and more number of recordings, surely your rejections may be somewhat reduced, right? So do you understood the t-test, how it is working? We will have more examples also. Have you understood the t-test?
As confidence increases, region decreases, no sir.
Yes, come again.
As confidence increases, the gray region decreases, no sir.
As confidence increases,
Gray region, sir, acceptance region.
yes,
It
you
will
can
decrease or
actually do that.
increase, sir.
See, this confidence interval is actually present in 95%. If you go to the T table, I'm having here, if it is actually not only dependent on this, if the number of observation is increasing, surely see it is actually having some decreasing trend. When the number of observation is there, and if I fix the same confidence interval, it is actually decreasing. And if I have only 90% confidence also, see here, it is actually having some lesser values. So this actually will move. For example, T point 2.776. If you say it is 90% confidence, the reject this gray region will shrink. If you have 100% confidence, a gray region will be only this much. This much only the gray region will be there. All are rejections only. So if I decrease the confidence in, and if I make only 50% confidence, then what will happen is the gray region will be like this here and here. More sorry, red region will be this, and all these will be gray if you have only 50%. But it is not advisable to take that 50% confidence and all. You have only this thing. See, you have either 90, 95%, 98%, 99%, and this is 998%, 999%. Only these levels you are having. See. From this only you can select.
Okay, got it, sir.
Yes. Okay, so far so good, right? Now we understood the t-test. The main thing to go for t-test is for checking the null hypothesis. I'll write it here also. So if I want to reject the null hypothesis, surely I require something like t-test, which will help me a lot, right? There are many other things and the statistical things, and what I'm solving here, it is not in syllabus, but it is actually necessary to understand the t-test when we go for machine learning examples. Not only learning algorithms, when you go for correcting the errors, need to understand these hypothesis examples also. There are many other tests for doing this. Other is F test is available, chi-square test is available. Many things are available based on the sample sets. For F test, we'll having the F table, and for chi-square, we have a chi-square tables available. So based on that, we'll be actually deriving out. These tables are actually predefined by those statisticians, and based on their recordings, they have built these tables, and based on these tables only we need to work. The best sample size is actually 20, right? So the best degrees of freedom is 20. You try to remember that the best degrees of freedom is 20, right?